that are surface orientable. And we're going to take alpha to be an essential simple closed curve in our surface. Then there's a quasi-isometrically embedded copy of z to the n in this graph, which I did not at all define for all n. And whenever we have a qi embedded copy of z to the n, well, we know that our space is not hyperbolic. So we're going to take a few minutes to define what on earth this graph is and how is it related to some other graphs that have been studied more frequently. Great. So let's begin with a brief history of curve graphs and fine curve graphs. So the curve graph of a surface, and we denote it C of S, is a graph whose vertices are isotopy classes of essential simple closed curves, and whose edges connect isotopy classes that admit disjoint representatives. And here's a little bit of a snippet of the curve graph based on this surface. So there have been many people who have studied the curve graphs, including but not limited to like Hare, Ivanov, Masur, Minsky, Harvey. So many people studied curve graphs, and in particular how we could use curve graphs to learn about mapping class groups. But more recently, people have introduced the fine curve graph of a surface, which we denote script C with a little dagger on top of S. And now vertices, instead of being isotopy classes of essential simple closed curves, we have just the essential simple closed curves themselves. And now edges, instead of being between isotopy classes that admit disjoint representatives, they just connect curves that are disjoint to begin with. So whereas the curve graph is countably infinite and locally countably infinite, the fine curve graph is a lot wilder, because we have an uncountable number of curves on a surface, and each curve has an uncountable number of neighbors. So the fine curve graph was first introduced by Bowden, Hensel, and Webb in the case where vertices were taken to be smooth curves, and they used the fine curve graph to prove that diff naught of a surface is not uniformly perfect, which is very different from diff naught of manifolds of other dimensions other than 4, because we still have no idea what happens in dimension 4. But when we go from the curve graph to the fine curve graph, we have or rather from the fine curve graph to the curve graph, we hide some information. And in particular, to get from the fine curve graph to the curve graph, we collapse subgraphs corresponding to isotopy classes, to entire isotopy classes. And so we might want to know more about these subgraphs that we're collapsing. So one question that we could ask is, what is the geometry of these single isotopy class subgraphs? And we're going to denote them C with a little dagger on top, because it's a subgraph of the fine curve graph, and a subscript of alpha, where the alpha is corresponds to the isotopy class we're concerned with. So it's a curve, and we're looking at the subgraph induced by its isotopy class. So now I'm going to take, before that, first, we do have a history of studying hyperbolicity in curve graphs and fine curve graphs. So the curve graph was first shown to be hyperbolic by Masur and Minsky, while the fine curve graph was shown to be hyperbolic by Bowden, Hensel, and Webb. And lots of related graphs and subgraphs are also known to be hyperbolic. And so now we ask, is the single isotopy class fine curve graph hyperbolic or not? So what I'm about to do is I'm about to try and convince y'all that this single isotopy class subgraph is hyperbolic, and then I will try to convince you that it is not hyperbolic, and then we're going to see what wins. All right, so the first thing is, well, should I believe that this subgraph of the fine curve graph is hyperbolic, well, maybe we can say it's hyperbolic if it acts similarly to the entire fine curve graph. So in other words, can curves in one isotopy class kind of mimic how curves in other isotopy classes behave? And well, they can to some extent. So for example, if we take this blue curve and we push all the way around about this orange curve, we get something that kind of looks like the orange curve. And what more, if you have that two curves fill a surface, so when you cut them up, cut the surface up along the curves, you get a union of disks and punctured disks. Then if you take the first curve and that same curve, but pushed along the second curve, so kind of like this red and this blue, they will also fill the surface. So you have this similar idea of like two curves in the same isotopy class can fill a surface. So for this reason, we might say like, hey, the curves in the isotopy class of the blue curve, they look like curves, like all the curves on the surface, more or less. And so maybe they act like all the curves on the surface. So these are reasons that I believe that maybe we should believe that this graph is hyperbolic. And now I'm going to try and convince you that it's not hyperbolic, or maybe that the yes isn't so strong. And here's the main idea. If we have this blue curve, for example, no matter how we try to isotope the blue curve, no matter how crazy it gets, part of the blue curve will always be left behind in this yellow region. So somehow we can't escape like part of the surface if we're a curve. So we can't completely mimic other curves because we always retain some of the information of the original curve. So given this, is the subgraph hyperbolic? And well, the answer is no, because of the main theorem that I said on the first slide. We have that there's a QI embedded copy of z to the n for all n in the single isotopy class subgraph, and therefore it's not hyperbolic. So let's see where all this comes from. Let's see a proof outline for the special case. Right. So our goal is to find a quasi-isometrically embedded copy of z to the n. And QI embedded means that distances are changed at most linearly by our math. So we're looking for some inequalities, in other words. So these kinds of linear inequalities. And let's see where we might be able to get these. In particular, we're interested in distances. So we want to figure out how do we understand distances in the single isotopy class fine curve graph. So we want to bound on distances from below and from above. So we're going to take a little bit of a detour into talking about subsurface projections. So let's say we have this red curve and this blue curve, and we want to know what the distance between them is. And we're going to totally ignore the fact that it's 2, because that was a mistake on my part. So let's say it wasn't 2. And what is a way that we can bound the distance? Well, one way we can bound the distance is we can take a subsurface of our entire surface, so let's say this upper half, and we can look at the projection, and the projection is a set of curves and arcs. So it's kind of like you don't get a single curve or arc, you might get multiple. And in that sense, we no longer look at a curve graph, we might want to look at the arc and curve graph of this little subsurface. Now, if we have a path in the curve graph of curves that all of which intersect T, so this upper subsurface, we can take a projection of every single one of those curves to T, and we get a path between the projections of the first curve and the last curve. So in other words, if we have that everything along a path intersects t, we can bound our distance from below by distances of the projections of our curves to t. All right. So in other words, we can use like inescapable subsurfaces as a way to get bounds on distance. So somehow, well, inescapable subsurfaces, that was mentioned somehow before, but now we want to get n involved for any n. And so the first step to our proof is going to be to find n annuli, which we're going to call ti. And these have to be special annuli such that every curve isotopic to alpha intersects all of them. So in this case, not too hard to find. We can have just a bunch of annuli, parallel annuli here, and a curve alpha around the center if, for example, alpha is not separating. And so the special thing is that every curve isotopic to alpha also intersects all of these annuli. So that's step one, finding the n annuli. And step two is finding a nice homeomorphism that mixes up each annulus. And so the goal is we want to use subsurface projections to show that if we apply this homeomorphism many, many times, somehow the image of the projection of alpha, or rather just alpha, the image of alpha is far from alpha to begin with. But what does it mean to mix an annulus a bunch? What does it mean to really deform an annulus? How do we even get bounds for an annulus because it's such a simple subsurface? So here's the main idea. We're going to add a few punctures to our annulus to make it less of a simple surface. And we're going to translate this into a problem about arc graphs. And in particular, this is a problem about surviving arc graphs, which I'm not going to define, but you can think of this as a subgraph of an arc graph. Okay. So the first thing we're going to do is we're going to take a curve that now fills our surface, and we're going to take a point push about this curve. So in this case, what does a point push look like? We're going to start down there, and we're going to start pushing our surface along this curve until we get back to the beginning. And something that now seems a lot more reasonable is the belief that this point push, just point pushing once along this curve, actually messes up our annulus a lot. And so it's potentially believable that the image of any projection of alpha, so for example, this original arc that was vertical, is far from its image under this homeomorphism. And in fact, it is pretty far. So we have some kind of bounds using arc graphs. Okay. So overall, after a homeomorphism, alpha intersects phi of alpha a lot. And so our hope is that phi of alpha is far from alpha in the single isotopy classifying curve graph. But behind the scenes, what we're actually doing is translating between around 5 different graphs. And this is just something I'm omitting here. So we're going from curve graphs to arc graphs to surviving arc graphs to fine arc graphs, and finally to our single isotopy classifying curve graph. Okay. So our actual claim here then is that a map from Z to the N to the single isotopy classifying curve graph given basically just by taking all the coordinates and raising the phi to the power of the coordinates is a QI embedding. Well, to show something is a QI embedding, we need a bunch of inequalities. So something that it's going to end up looking like this. And those are inequalities. So the ones that we focused on today, which I call interesting inequalities, which is a matter of opinion, but not really, is first our translations between the graphs happen in this step, and our subsurface projections happen here. Some other inequalities are involve playing with numbers, using the triangle inequality as is, we have to, and using some information about surface dynamics and isometric actions. Okay. So I mentioned earlier that this is actually a special case, but what did we actually use in our proof? We used that every representative alpha intersects the annuli in an essential way. So every representative alpha has to intersect every single annulus. But there are lots of other curves that also essentially intersect all of these annuli. So really, we can take all the curves that intersect the annuli, essentially. And what does this give us? If the core curves of like the annuli is beta, for example, in the curve complex, we want not the things that are disjoint from it, so not the things that are distance 1 from the core curve of beta, but everything distance at least 2. And all of these curves, all the curves corresponding to these isotopy classes are curves that we can include in our new subgraph of the fine curve graph. So these are all going to be curves that intersect these annuli essentially. So now we have a new graph. It's going to be the graph. Well, we're going to take this script B, which is everything distance at least 2 from some curve beta, and we're going to take let script A be a connected subgraph of B, and we're going to take the subgraph or the subgraph of the fine curve graph induced by the range of alpha, or not alpha, of script A. So that's a typo. I apologize. And in this case, this QI embedding of Z to the N into this much larger subgraph of the fine curve graph is also a QI. And this much larger subgraph is also not hyperbolic. So we have, in other words, this very not hyperbolic subgraph of the fine curve graph, but it's also a very big graph. Right. But moreover, we have a second corollary, which is that our hyperbolic space, which is the fine curve graph, can be covered by 2 non-hyperbolic spaces. And these 2 non-hyperbolic spaces really kind of intertwine in a way. So in particular, we're going to take alpha 1 to be B, the script B, and alpha 2 to be, all right, this is an interesting thing. Basically, we just take beta, and we're going to take some curve further from beta, maybe like out here, and we're going to take the 2 and everything distance at least 2 from here as well. So that's going to be script A sub 2. So script A sub 1 is hyperbolic by our original by our original theorem, and script A sub 2 is also hyperbolic by our original theorem. It's just everything that's avoiding some other like subgraph, and they union to the entire fine curve graph. So thank you, and that is your theorem.
Okay, let's thank Roberta. Any questions? I guess one thought I had, which I don't know, maybe seems surprising, is also not just that it's not hyperbolic, but that it's infinite dimensional in some sense, maybe asymptotic dimension. I don't know, does that suffice? Yeah, I don't really know. It's not really a question. It just seems sufficing to me.
Yeah, it was really surprising to me as well at first. But I ended up being okay with it. And I'm pretty sure it's much more not hyperbolic than just c to the n. Like I'm pretty sure that all like infinite sequences, like the space of infinite sequences that are eventually zero, also QI embeds. But that is not officially written up yet. So you did not hear it from me, I say, in a recorded meeting.
I'm not sure if that's a question, but any other questions?
Yes, I have a question. Roberta, so you have QI embeddings, but these embeddings are not equivariant for the isometric group of the fine curve graph, or you can find. Maybe a question if this says something to the isometric group of the fine curve graph for an isotopy class.
Could you please repeat that?
Yes, so I mean, you have a QI embedding, but this QI embedding is not coming from seeing C to the n inside the isometric group of the curve graph.
Oh,
Of
so
the
not
fine curve
inside
graph of
the
isotopy class.
automorphism group?
Yes,
Or-
yes, the automorphism group. Yes, if this
Yeah.
says something to relate to the automorphism group, that's my question.
Yeah, so we were interested also in like the automorphism group of this of these types of subgraphs. And I think there's something to be said of it not being super easy to figure out.
Thank you.
Anyone else have any questions? Okay, so if not, let's thank Roberta again.